Thank you for the introduction. And it's my great honor to have this talk opportunity. And the title of my talk is Human-in-the-Loop Preferential Bayesian Optimization for Visual Design. So let me begin with a quick self-introduction. So I'm Yuki Koyama, and I'm a researcher at ICE, which is a Japanese National Research Institute. And as a second affiliation, I recently joined Graphinica, which is a Japanese animation studio. And my research area is the intersection between computer graphics and human-computer interaction. And in this area, I have worked on computational design and human-in-the-loop optimization, and digital fabrication, and so on. And here is the outline of this talk. So first, I'd like to explain the motivation of why we need to consider human-in-the-loop optimization. And then I'll talk about Bayesian optimization, which is what I have been working on recently. Then I'll explain the details of our two recent SIGGRAPH papers that are based on Bayesian optimization. And finally, I'll summarize the talk. Okay, so let me begin with the motivation for human-in-the-loop design optimization. The parametric design is the design problem where the design variation is determined by a set of parameters. And the goal is to find the best parameter set. And many content creation scenarios involve parametric design. For example, photo color enhancement is one of the most popular scenarios. For example, Photoshop has many sliders that should be adjusted carefully to make the target photograph look best. The goal of such parametric design is to find the best parameter value combination that provides the best design. For this purpose, the designer has to perform many trials and errors manually. This manual procedure has an analogy to mathematical optimization procedure where the system performs trials and errors using some iterative algorithm and finally finds the maximizer of the target objective function. So this viewpoint facilitates computational design research where design problems are formulated as mathematical optimization problems, and the problems are solved by computational techniques such as numerical optimization, machine learning, and so on. So I have been working on such computational design research. For example, we worked on computational design of freeform model airplanes, where we solve an optimization problem to maximize the flyability of the user-created airplane. We also worked on designing haptic force feedback by embedding magnets into fabricated objects. So in this work, we formulated an optimization problem to search for optimal magnet positions and orientations that can reproduce target haptics. And I have worked on some other projects as shown here. In these projects, the design goal was the functionality of designed objects. And similarly, many researchers in the computer graphics community have formulated various functionality of designed objects and solved optimization problems. However, when considering about design goals in practice, functionality can be just one aspect of design goals. And another missing aspect is the subjective preference. And in many scenarios, it is natural to consider the preference as a design goal. And for the functionality, we can compute the goodness of a design by using predictive simulation, like using physical simulation. On the other hand, for the preference, it is difficult to compute the goodness of a design because preference is a perceptual metric. So we need to incorporate human assessment somehow into the optimization process. So in other words, it means that the function G is perceptually defined, so only human knows about this function shape. So the challenge is how can we solve this optimization problem by effectively using human assessment. So as an answer for this question, I'd like to introduce human-in-the-loop optimization. So human-in-the-loop optimization can be used for solving design problems with subjective or perceptual objective functions. So in this case, the machine processor iteratively asks the human evaluator about subjective questions. And then the human evaluator provides some feedback based on his or her perception. And through this iteration, the machine processor finally finds the maximizer of this unknown objective function. When taking this approach, we need to care about some points. The first point is about the query design for human evaluators. So generally speaking, we should avoid absolute assessment or absolute scoring because the human evaluator cannot reliably answer the precise value. For example, given a single photograph, asking the human to provide a single precise score like this is not a reasonable way. Instead, we can use a relative assessment. So the human evaluator can stably answer which option is better among two or possibly more options. For example, if there are options A and options B, and the user chooses A in this case, then we can get relative information that the objective function value for A is larger than the objective function value for B. So this is the first consideration that we need to care about. And the second consideration is the number of queries. So when having human in the loop, the number of total queries should be sufficiently small. For example, not like 1,000. So this is because human evaluators are prohibitively slow compared to typical optimization settings using machine processors. And another reason is that human evaluators can simply get tired if asked so many times. So taking these 2 points into account, in this talk, I'd like to introduce a technique called Preferential Bayesian optimization. So Preferential Bayesian optimization, or PBO in short, is a powerful technique in this setup. So PBO is an extension of Bayesian optimization, or BO in short, but tailored for human-in-the-loop settings. And the benefits of PBO is that first, PBO can proceed with the optimization steps using relative assessment queries, unlike typical optimization algorithms. So we don't have to rely on absolute scoring. And second, PBO can find a good solution with only a small number of queries. And thanks to these two benefits, PBO is very powerful in human-in-the-loop settings. Our two papers are based on the preferential Bayesian optimization, but before explaining about PBO and these two works, I'd like to talk about the standard Bayesian optimization first. Okay, so what is standard Bayesian optimization? So suppose that we have an objective function f, which looks like this slide, but we don't know its analytic formulation explicitly. So what we can do is to provide some x and then observe the function value fx. The goal is to find the maximizer of this unknown function by solving this maximization problem. This is called a black box optimization problem, and we cannot observe its gradient, and the function may have multiple local maxima. The challenge here is the way to sampling the points. So one naive strategy is to randomly sample many points and then find the point that provided the largest value. However, when the problem is multi-dimensional, then this naive approach is not feasible because the search space becomes too large. So we want to minimize the number of necessary sampling points by some intelligent strategy. And Bayesian optimization is a powerful choice for this kind of problem. So BO is a global black box optimization algorithm, and it can find optimal solutions with only a small number of function evaluations. This property makes it useful to manage expensive to evaluate objective functions. For example, this technique is used for hyperparameter tuning for deep learning models. And recently, it was used for fabrication in the loop object design, and so on. And to intelligently sample points, BO uses acquisition functions. An acquisition function is a function that evaluates how effective a given point is if it is sampled in the next iteration. And the point that maximizes the acquisition function will be sampled in the next iteration. Acquisition functions are designed to automatically balance the exploration and exploitation. Exploration means it prioritizes the region with large uncertainty, and exploitation means that it prioritizes the region with high predicted value. For example, in this image, the acquisition function value is large, around like 0.25, because both the predicted value and the uncertainty are large around here. Okay, so let me explain its behavior step by step. So suppose that this is the unknown objective function. And for the first iteration, we choose an arbitrary random point since we have no information yet. Then BO tries to best estimate the landscape of the unknown objective function using the observed data. And for this estimation, the technique called Gaussian process regression is often used. Using this estimated function, BO calculates the acquisition function. And then it finds the maximizer of the acquisition function. And then in the next iteration, this point is observed. Using the two observed data points, BO updates the estimated function and also the acquisition function, and then finds the maximizer of the acquisition function and then observe this point. So this procedure is repeated several times like this. And in this case, we could find a very nice solution with only 12 iterations, which is very efficient. So this is how standard BO works. And now let me go back to the explanation of preferential Bayesian optimization. So PBO is an extension of BO, and it runs with relative assessment queries instead of absolute assessment. So we can use PBO with human evaluators effectively. And similar to BO, PBO can also find optimal solutions with only a small number of preferential feedbacks. So this property is very important for us because human is expensive to query. And for modeling the probability of relative preference data, we can use the model called Bradley-Terry-Luce model. We use this model with the map estimation method to determine the latent goodness value. So please refer to the details for this part. Refer to the paper for details of this part. So this slide shows how PBO works in a simple 1D problem. In this case, we use pairwise comparison in which we compare the current best point and the maximizer of the acquisition function. For the first iteration, we randomly sample 2 points and then compare them to determine which is higher. Then we calculate the acquisition function and determine its maximizer. Then this point is compared with the current best point in the next iteration. Then the system updates the predicted function shape and also updates the acquisition function. Then find the maximizer of the acquisition function and then use this point in the next comparison. So this procedure is repeated several times. And in this case, we could find a very nice solution within only 8 iterations without using any absolute assessment, but using only relative assessment. So this is how PBO works. Okay, so now I'd like to explain our work. So this work extends PBO for more efficiency and applies it to design problems in computer graphics. And this work was published at SIGGRAPH 2017. So in this specific work, we made 2 contributions. The first contribution is the concept of crowd-powered or crowd-in-the-loop design optimizer. So this optimizer solves optimization problems using crowdsourced human computation. The second contribution is the technique called sequential line search, which is the new extension of preferential Bayesian optimization that is even more efficient. So this shows the concept of our crowd-powered optimization solver. So suppose that there is a crowdsource button in the design interface and the user can push it when necessary. Then the tool runs the optimization process in the backend, and finally the user can obtain the optimal slider values. So this is enabled by decomposing the original high-dimensional search task into a sequence of line search microtasks. The line search task is much easier than the original high-dimensional search task and can be easily performed by crowd workers. And after some iterations, the system finds the optimal parameter values in the original high-dimensional search space. And this algorithm is called sequential line search. The key idea is to use a microtask design that is different from the previous work. The previous work used the pairwise comparison query which can be the simplest assessment, relative assessment task. And instead, we propose asking crowd workers to perform a single slider manipulation task, which is sufficiently easy, and this is still considered as a relative assessment. And this microtask design provides much richer information than pairwise comparison, and so the optimization can converge much, much faster. The challenge here is the definition of the one-dimensional subspace that will be mapped to the slider in each iteration. And for this, we extend PBO to determine this slider space for each iteration. So we construct this slider space as follows. So first, we set one endpoint to the point called X plus, which represents the best point observed so far. And second, we set the other endpoint to the point called XEI, which is the point that maximizes the acquisition function. And note that we used the expected improvement as an acquisition function because this is the popular choice. Then by connecting these 2 points, we construct the one-dimensional slider space. And here is an example optimization sequence. So suppose that we want to find the maximum of this unknown two-dimensional function. And first, the system generates an initial slider space randomly, just randomly, because there is no information yet. And the system asks human evaluators to perform a line search task using this space and obtains the point called X chosen, which represents the maximum in this subspace. By using this information, the system updates the internal models, and especially the system obtains X plus, which is the current best point, and XEI, which maximizes the expected improvement or the acquisition function. By connecting these 2 points, the system determines the next slider space. And by using this space, the system queries line search and then obtains X chosen. And by using this observed data, the system updates the internal models and especially obtains X plus and XEI. And by connecting these 2 points, the system determines the next slider space and then obtains X chosen by line search. The system iterates this process until a good solution is found. And this solver can be applied to various parametric design scenarios because it is domain agnostic. So here we applied it to photo color enhancement. So this slide shows the original input images, and this shows the results of the crowd in the loop optimization solver. Okay, so let's see again. So this shows the original input images, and this is the results. So I hope you can see some improvement. So to evaluate the quality of these results, we conducted a simple experiment in which another set of crowd workers were asked to vote for the best image among several options. And this shows the result. The leftmost image is the original one, and the second left is produced by our method or the crowds. And for comparison, we also show the results of auto enhancement by Photoshop and Lightroom. And this is another result. And overall, the crowds preferred the results generated by crowds. So we consider this result is very reasonable because the crowd-powered solver can produce a solution that is people's choice. So it is natural that people prefer them. So this demonstrates one of the advantages of having crowds in the loop of the optimization. And this solver can be used for different scenarios such as shader parameter adjustment. Okay, so since our method uses human intelligence inside, so we can just specify reference photographs to obtain corresponding parameters. So these are the results. The top image is the input reference photograph, and the bottom image visualizes the material obtained by the optimization. So thanks to crowd's intelligence, we can use this kind of fuzzy, very fuzzy inputs. Okay, so we evaluated this method by comparing it with some baselines, but I'd like to omit the details, but the conclusion is that our method was much faster than the other baselines, including the previous work using pairwise comparison. So in this work, we proposed a new efficient human-in-the-loop optimization framework that is based on preferential Bayesian optimization. And the line search task, the design of line search task was simple enough for crowdsourcing and was useful to reduce the number of necessary iterations drastically compared to the case of using pairwise comparison. And human-in-the-loop systems need human evaluators. And based on the types of evaluators, we can roughly classify human-in-the-loop systems into two categories. The first one is crowd-in-the-loop optimization system, as seen in the previous slides. And in this case, many paid crowd workers are repeatedly asked to perform perceptual microtasks. And one constraint is that the task design should be sufficiently simple so that crowd workers can easily and stably perform. And the other one is the user-in-the-loop optimization, in which the single user is repeatedly asked to perform perceptual assessment interactively. And in this case, the task design can be a little more complex compared to the crowdsourcing setting. Okay, so now let me show our recent work about user-in-the-loop optimization. So this work was published at SIGGRAPH 2020. So in this work, we take a user-in-the-loop approach and propose a system called Sequential Gallery. So again, our target problem is tweaking a set of design parameters. So we want to find an optimal parameter value combination that provides the best look. So Sequential Gallery is an interactive optimization system that can be used for this kind of problems. So first, the system shows options to the user using a grid interface, like this one, and then asks the user to choose the best option in this grid based on the user's preference. Then the system updates the options shown in the grid view, and again asks the user to choose the best one from the grid. So this process is iteratively performed several times. And finally, the user can obtain the optimal parameter set. Okay, so the key point is in the query design. Okay, so in the previous work shown in the center in this slide, we used a slider interface to let evaluators explore a one-dimensional subspace. So this was the key to reduce the number of necessary iterations compared to the case of using pairwise comparisons. And in this work, as shown in the right in this slide, we let evaluators explore a two-dimensional subspace. Because 2D search query can provide much more information than a 1D search query, this makes the number of necessary iterations even smaller. And an additional benefit is that this 2D search query has a good compatibility with grid interfaces. Okay, so now let me explain the workflow of this system. So suppose that this is the 2D subspace that the PBO algorithm determines. Then the system asks users to select the best one from the grid. And based on this preferential feedback data, the new PBO algorithm determines the next search plane. Then again, the system asks the user to select the best one from the grid. And using all the accumulated preferential data, the new PBO algorithm determines the next search plane. And like this way, the system proceeds the iteration. So we have some benefits of using this grid interface. For example, it allows the user to easily grasp the available options in the current 2D subspace by just looking at the grid view. And also, since its interaction is WYSIWYG, which means what you see is what you get, the user does not need to be familiar with the original parameters or raw parameters. But one question would be, how can we determine the next plane in each iteration? So in each iteration, we want to select the most effective 2D subspace or search plane for the next query. The question is how to evaluate the effectiveness of a given plane. And for this, we extend the acquisition function used in the standard BO. The existing acquisition function used in standard BO is pointwise. That is, it takes point X as input and calculates the effectiveness. Then we propose an acquisition function that is plane-wise. That is, it takes a plane as input and calculates the effectiveness. So we propose to define this as a surface integral of the pointwise acquisition function. And using this definition, now we can choose the next plane by solving this maximization problem. Note that this maximization is very easily solved by using standard gradient-based optimization techniques such as LBFGS. Okay, so now I'd like to talk about the applications. The proposed framework is domain agnostic, so it can be applied to various parametric design scenarios. And this shows the result of photo enhancement controlled by 12 parameters. This is the user interface of the system. The task for the user is to choose the best option from the grid by clicking it. So one of the benefits of this grid interface is that the user can easily understand what variation is possible in the current subspace. So with our system, the user can easily and quickly compare different color variations and pick up the most preferable enhancement. And after several iterations, the user can obtain the optimal parameter set that provides the best enhancement for the user. Next, we show another application on 3D body shape modeling using a pre-trained model. So here, the user needs to find a 10-dimensional vector that generates a desired shape. And here, suppose that the user wants to create a character from a fictional novel that is given this text description of a fictional character. The user generates an appropriate body shape for this character. Or in other words, the user expresses the mental image of this fictional character. And in this case, after 7 iterations, the user got this model from this text description. Okay, so we evaluated the performance of the proposed method. So in this experiment, we considered these conditions, these 3 conditions. The first 2 are the baselines, and the last one is the proposed algorithm. The first baseline is a sequential line search from the previous work. And the second baseline is similar to the proposed method, but the plane is randomly chosen instead of based on the acquisition function. And here are the results using synthetic test functions. So these plots indicate that our method, indicated by green, consistently outperformed the other baselines. So in this work, we proposed a novel user-in-the-loop Bayesian optimization algorithm combined with a tailored grid interface. And we demonstrated that it could efficiently solve perceptual design problems. The most important point is that this efficiency was achieved thanks to the tight integration between algorithm design and interaction design. So this indicates that we need both computational viewpoint and interaction viewpoint to investigate this research direction. Okay, so before summarizing this talk, I'd like to mention some of our more recent projects. So this paper is about applying the human-in-the-loop Bayesian optimization to melody generation using a deep generative model. So the system provides multiple candidate melodies using Bayesian optimization, and then the user selects the best melody from the candidates. The pilot study suggests that this framework has the potential to lower the barriers for novice composers. And the next one is a follow-up work of the previous generative model melody composition project. So in this work, from the HCI viewpoint, we investigated the effect of allowing users to manually control the exploitation balancing in Bayesian optimization. The user study suggests that this additional control for the user can help improve the user engagement in this design session. And the next one was published at SIGGRAPH 2020, and we proposed a human-in-the-loop optimization method for content creation using deep generative models such as GANs. So in this case, our method does not use Bayesian optimization, but instead, the method analyzes the local structure of the deep generative model to construct the effective subspace for the slider manipulation query. So the interface is basically the same as the project that I explained first. Okay, so now let me summarize this talk. So today I talked about human-in-the-loop optimization, which can be used for solving problems with perceptual objective functions such as preference. And then I introduced preferential Bayesian optimization as a powerful technique for this purpose. And it can reduce the number of necessary queries, which is important because human is expensive to evaluate. And also it can use relative assessment, which is important when we ask human to perform perceptual evaluation. And as we saw in the two projects, tight integration between algorithm design and interface design would be the key to achieve higher efficiency in the human-in-the-loop optimization systems. And finally, the source codes are available for C++ and Python users at GitHub, so please check it. And I'd like to thank all the collaborators. So, okay, so that's it from me. So thank you very much.
Thanks, Yuki. I have a question about the Bayesian optimization. So in the talk, you showed very nice examples with dimension less than 20. So I'm wondering whether it is possible to apply the PBO to problems with higher dimension, such as hundreds or even thousands. Okay.
Yeah, this is a very important viewpoint and very important question. So actually, Bayesian optimization has a limitation about the target dimensionality. So sorry, let me show a slide. So okay, so this is an appendix slide. So actually, it is known that Bayesian optimization does not work well with very high dimensional spaces, for example, with more than 20 dimensions. So this is a known issue. So I'm not sure whether some theoretic analysis exists about this issue, but anyway, we have to avoid to apply BO directly to very high dimensional problems. So one possible solution is to first apply some dimensional reduction technique and then use BO in the reduced space. And we actually took this approach in our previous project, and it works very well. But obviously, we have a trade-off between the low dimensionality and the model expressivity. So that's one possibility. And another possible solution is to incorporate some additional information to guide the Bayesian optimization, the sampling behavior of the Bayesian optimization. And for example, Chong et al. Proposed a method, BO method, where the user can guide the sampling behavior by sketching or specifying some soft constraints in the sampling. Thanks to this guidance, they successfully applied BO for GAN image generation from the more than 500 dimensional space. So yeah, this is another possible solution. Yeah.
Yeah, I see. Yeah, for that case, I think the dimension reduction as well as additional inputs would be very helpful to solve this this dimension problem. Okay. So another question is related to the user. So if I understand correctly, so it seems that in your methods, you assume that the user never changes his or her preference. Okay, so the user must behave consistently during the design optimization process. So I'm wondering, so if you can extend your method to deal with changing preference. Okay, so usually, so if we require the user to behave consistently for a very long design process, this may be too much. Okay, so if you somehow you can extend this method to deal with the case, it will be great. Yeah.
Yeah. So yeah, this is also an important viewpoint. So Bayesian optimization does not, Bayesian optimization does require the objective function not to change during the optimization. So this means that we assume that the human evaluators behave consistently and do not change their preference. So this is the basic assumption that we made. One possible approach to support such preference change is to detect the timing when the preference changes somehow, and then discard all the accumulated data obtained before the preference change. So that's a simple approach to solve this problem, but more smart approaches should be investigated in the future work, I think.
I see. Yeah, thanks for the explanation. So let's see if there are questions from the audience. Okay, it seems that we don't have any further questions. So I think this is the end of this webinar. So thanks again to Hongbo and Yuki for the very nice talks. And also thanks everyone for attending this webinar and watching the live streaming on YouTube and Huya. Okay, thank you.
Thank you very much.
Okay, yeah, bye-bye.
Bye-bye.